classical plate bending elements. So now in this we are first going to consider classical plate theory. So what I am saying is that suppose now we have a plate like this. So this is a plate and it has certain thickness. The coordinates are say x and y in the in-plane direction and z is along the thickness direction. And say h is the thickness of the plate. So thickness of the plate is h. And this is the coordinate system we are considering. Now in the classical plate theory, we assume that normal to the middle surface. So say suppose if this is the middle surface and this is normal to the middle surface, so this normal remains straight, normal remains straight and normal to the middle surface after deformation. So that is the main assumption of the classical plate theory. So that means now in the deform configuration, and of course there would be loading, so the loading is in the transverse direction. So let us say that load is q, and when under this application of this load, when this plate deforms, so let us say this edge becomes something like this. So if we look at the normal, the deformed middle surface will go something like this, and the normal which was initially this normal, now that normal becomes it remains normal and straight. So now in the deformed configuration, this is the normal, so this remains normal and straight, and this angle, so if you look at this particular angle, this angle would be del w by del x, where w is the transverse displacement. So similarly, if I see from the this is by looking this phase, if I that is looking at the xz phase, if we look at the yz phase for example, so this is the yz phase, and let us say this yz phase deforms like this. So the deformation of yz phase is like this, and the middle surface would be something like this. So we have a normal here, this normal, that normal becomes like this. So again at this point, this angle, if you look at this angle, this would be del w by del y. So now if you look at the displacements, so basic idea is that we start with the displacement. So if you look at the displacements, so we have the displacement along x direction. So say u, which is a function of x, y and z. So u will be equal to, so if you look at the xz phase as I explained, so let me draw separately that xz phase. So this is the xz phase, this is the middle surface, then it deforms like this, and then let us say now we take this normal, which remains normal to the middle surface, so that means this angle remains 90 degrees, but this has rotated by an angle del w by del x, and this distance from the middle surface is z. So if you look at this distance at any point, so this distance would be equal to z into del w by del x. So that is displacement along x direction. Now this is along the negative x direction, so we will have minus z into del w by del x. And similarly the displacement along y direction at any point x, y, z will be equal to, similarly if we look at Now, as I said, now we looked at the other phase, YZ phase. So this is the YZ phase. This is the center line, and then now this deforms, say something like, no, it deforms like this, and this is the middle surface. That normal initially, let us say the normal here is like going like this, and finally, that normal to the middle surface is this, and this angle is del w by del y. So this will be the displacement along the negative y direction, and this would be z into del w by del y. So this is minus z into del w by del y. And of course w, so u is the displacement along x direction, v is the displacement along y direction, and w the displacement along z direction is independent of z, so it's only function of x and y. So these are the three displacements, but you see all three are no in terms of only one unknown, that is w, which is a function of xy, because u and v are written in terms of the derivatives of w itself. So here the basic assumption is that a straight normal to the middle surface remains normal and straight to the deformed middle surface. So straight normal, the main assumption here is that the straight normal to the middle surface remains straight and normal to the deformed middle surface. Hello, am I audible? Hello.
You are audible, sir.
Yes, sir.
And is the screen visible?
Yes, it is.
So now in this case, basically we look at the displacements UVW are written only in terms of W. So only one unknown we have in this problem, that is actually W. So these are the displacements. So this is known as classical plate theory. So in the classical plate theory, and of course this is the essentially the result of a thin plate. So thin plate means, if we look at this dimension, let us say this dimension is A, and say no, this dimension is B, and thickness I have already assumed. So this will be applicable for thin plate. And thin plate means, if I look at either A by H or B by H, so A by H or B by H are greater than 20 for isotropic plates. Of course, for composites, this number may go to the higher side, but for isotropic plates, this A by H or B by H, if it is greater than 20, we can use classical plate theory. Or in that plate, the straight normal to the middle surface will remain straight and normal to the deformed middle surface after the application of the loads. So in that case, we can express the displacement in this manner. So this is known as classical plate theory. So we are going to discuss classical plate theory or classical Kirchhoff plate theory. So in this, basically the transverse shear strains are zero, and we call it as classical Kirchhoff plate theory. So now once you have these approximations for the displacements, then you go for the strains in the same sequence. So now if you look at the strains, epsilon xx would be, we know it is del u by del x, and u is minus z into del w by del x, so this will become minus z into del 2w by del x square. So this is similar to the Euler-Bernoulli beam theory. In the Euler-Bernoulli beam theory, the epsilon xx is minus z into d2w by dx square if you take z along the thickness direction, or if you take z y along the thickness direction, so then minus y into d2b by dx square. So basically this is similar to Euler-Bernoulli beam theory, and similarly the strain along the y direction would be del v by del y, and of course we are assuming that the displacement these curvature del 2w by del x square and del w by del x rotations are small, so the nonlinear terms in the strain displacement relations are neglected. So we have minus, this is z into del 2w by del y square, and the shear strain in plane shear strain, that is shear strain in the xy plane, will be gamma xy, and this gamma xy we know the expression del u by del y plus del v by del x. So see, del u by del y would be minus z into del 2w by del x del y, and del v by del x would be minus z into del 2w by del x del y. So this whole thing will be minus 2z into del 2w by del x del y. And if you look at the transverse shear strains, so if you look at the gamma xz is del u by del z plus del w by del x, and now u is minus z into del w by del x, so its derivative with respect to z would become minus del w by del x, so this is 0. Similarly, gamma yz, that is gamma xz is the change in angle between a line element parallel to x and z, and similarly gamma yz is the change in angle between a line element parallel to y and z. So these basically remain y and z, or x and z, after the deformation remain perpendicular to each other, so these strains are 0. So this would be del v by del z plus del w by del y as per the formula, so this is equal to 0. So you can see here that transverse shear strains are 0. So that's the basic assumption of classical Kirchhoff plate theory, that transverse so transverse shear strains are 0. If you also look at the epsilon zz, which is del w by del z, so since we have assumed w as a function of only x and y, so that will also be 0 from the theory. But for thin plates, it is more appropriate to assume the plane stress condition. So when we write the stress strain relation, we are going to use the plane stress condition. So there is a, although that contradicts uh, the basic assumption that w is independent of z, but that is what gives more accurate results. So we assume plane stress conditions. So these are the strains. So if you see, there are three non-zero components of strains, that is epsilon xx, epsilon yy, and gamma xy. Two normal strains and one shear strain in the xy plane. And so now if you look at the stresses, so now if you look at the stresses, so we are going to relate, because we want to do the displacement based formulation. So we want to express everything in terms of displacement, that is actually in this case w. So we have written strains in terms of w derivatives. Similarly, we want to write stresses in terms of strains and strain in terms of w derivatives. So for this, let me assume that the material is the plate material is linear, elastic, and isotropic. Although of course this can be extended to orthotropic materials, but we are limiting to this. And before I can write the stresses in terms of strains, let me also state that we are going to assume the plane stress condition. That is, we are going to take sigma zz as 0. So now for this, if you look at these stresses, in the last class also we wrote the stress strain relation for the plane stress case. So same relation you would have sigma xx. So sigma xx would be, we know that it is E upon 1 minus nu square into epsilon xx plus nu times epsilon yy. E is Young's modulus, nu is Poisson's ratio. So here if you see, this E is Young's modulus and nu is Poisson's ratio. So now if you look at sigma xx, if you put the values of epsilon xx and yy, expressions of epsilon xx and yy in terms of w derivatives, so we can write this as minus ez upon 1 minus nu square, and then epsilon xx is del 2 w by, here del square term will be there, and nu into del 2 w by del y square, minus z we have taken outside. So this is the expression for sigma xx in terms of w. So similarly, now if you look at the sigma yy can be written as, the basic expression for sigma yy is E upon 1 minus nu square into epsilon yy plus nu times epsilon xx. So this can be written as minus Ez. Now if you substitute the values of strains, you will have del 2 w by del y square plus nu into del 2 w by del x square. So these are the expressions for sigma xx, sigma yy in terms of w. Now if you look at tau xy, so tau xy, we know that it is g into gamma xy for linear elastic isotropic material, and g is E upon 2 into 1 plus nu. So this into gamma xy, and gamma xy is minus 2z into del 2 w by del x del y. So let me to keep the same form, whatever we have, minus cz upon 1 minus nu square and sigma xx and sigma yy. So we multiply numerator and denominator by 1 minus nu. So we can write this as minus E upon 1 minus nu square into 1 minus nu into z, and of course del 2 w by del x del y. So you know the expression for gamma xy, you put it here, multiply it by no whole thing by numerator and denominator by 1 minus nu. So you can write it as minus cz upon 1 minus nu square into 1 minus nu into del 2 w by del x del y. And so the other stresses, if you look at the sigma zz, sigma zz is 0. That's the plane stress condition we are assuming. So sigma zz is 0, tau xz is 0, because tau xz is g times gamma xz is 0. So tau xz is 0, and tau yz is g times gamma yz is 0. So tau yz is also 0. So these are the 0. Now in the plate theory, additionally, because now we are assuming, now see, the originally the problem is a three-dimensional problem, but then through the plate theory, classical Kirchhoff plate theory, we are writing the displacement in terms of as a linear u and v as a linear function subject. So kind of we are assuming the approximation of the displacement along the thickness direction. So u and v are linear in z and w is constant along z. So we are reducing a three-dimensional problem to a two-dimensional problem using classical Kirchhoff plate theory. So then in the plate theory, we also have the quantities called moment resultants. So let us define those also. So moment resultants. So moment resultants are the integrated stresses along the thickness direction. So we define one is mx. So mx is nothing but minus h by 2 to plus h by 2 z into sigma xx dz. So this we call as actually the moment resultant, mx, and I will tell you what is the physically what these moments are what. So this is going to be moment per unit length, per unit y length, moment per unit y length. So because it would be moment per unit length, so units would be Newton meter per meter. So that's the how it is coming, because this is a actually moment per unit length. So you have this kind of an expression. And if you put the expression for sigma xx in this, so you can write it as minus h by 2 to plus h by 2, and then we have sigma xx is minus ez upon 1 minus nu square. 1 z is already here, so we can write that as minus ez upon 1 minus nu square into del 2 w by del x square plus nu times del 2 w by del y square into dz. So now if you see del 2w by del x square and del 2w by del y square are only functions of x and y, so we can carry out the integration through the thickness. So we can write actually this expression as e into h cube. So integration of z square is z cube by 3, and then you put the limits minus h by 2 and plus h by 2. So we'll get ez cube upon 12 into 1 minus nu square into del 2w by del x square plus nu times del 2w by del y square. And so now this quantity eh cube upon 12 into 1 minus nu square is known as flexural rigidity. So we usually denote it by d. So we can write this as minus d into del 2w by del x square plus nu into del 2w by del y square. So you can say that mx is nothing but minus d. Let me write over here itself. So we can say here that mx is nothing but minus d into del 2w by del x square plus nu times del 2w by del y square. So where now if you look at this, d is eh cube upon 12 into 1 minus nu square, and it is known as flexural rigidity. Flexural rigidity. So this gives the basically stiffness against bending, so that is flexure, and that is why it is known as flexural rigidity. So this is the expression for mx, moment resultant mx. Then similarly we have, due to sigma y, we will have the moment resultant my. So similarly we have my. So my is integration minus h by 2 to plus h by 2 z into sigma yy dz. And now if you put the values, so you can see that this can also be written as minus d into del 2w by del y square plus nu into del 2w by del x square. So my can be written like this. So similar to it is similar to basic your mx. Now if you look at the mxy, because due to tau xy, when we multiply tau xy with z and integrate through the thickness, so we have another quantity mxy. So mxy is defined as integration from minus h by 2 to plus h by 2 z into tau xy dz. So now if you look at, if you put the values of tau xy, we have already written tau xy in terms of derivatives of w. So you can see that this can be written as minus integration from minus h by 2 to plus h by 2, and then you can write this as ez square upon 1 minus nu square into 1 minus nu into del 2w del x del y dz. So you will see that this can be written as es cube upon 12 1 minus nu square. So this is minus d into 1 minus nu into del 2w by del x del y. So this is mxy, the moment resultant mxy. The units of all three are Newton meter per meter. If you look at the the interpretation of these moment resultants, so let me draw a figure. So the coordinate axes are, this is x, this is y, and this is z. So when you look at the x face, this will be the middle surface. So x face, if I take a small the line here along the z direction, so this is the small line. In this line, the stresses, if you look at, one would be sigma xx, because this is having outward normal along positive x, so sigma xx is along positive x direction, and you will have tau xy, and tau xy would be along the positive y direction, so this is tau xy. So then what you are doing, you are taking this distance dz, so dz into sigma xx, and then you are multiplying by this distance z. So the distance from here to this point, this distance is z. So when you multiply sigma xx with z, it is going to give you moment about a moment about positive y-axis. So if you look at mx, the interpretation of mx, the expression I have already written, it is the moment per unit y length, moment per unit y length about positive y axis. Now similarly, if you interpret my, so my is on this phase. So let us say this is the middle surface, and if you take any line element here, this line element, in this line element we are going to have sigma, because outward normal is along positive y, so the positive sigma y is going to be in this direction, and then this is the distance z, this distance from here to here. So if you multiply this sigma y with z, you see that it is going to give you the moment about negative x-axis. So this is moment per unit x length about negative x-axis. So that is the interpretation of my. And now if you look at mxy, so mxy means if you look at this tau xy multiplied by dz and then z, so you see that this is going to give you moment about the negative x-axis. So mxy is the moment per unit, this is x length, no y length, per unit y length about negative x-axis, because this will produce the moment about actually this axis, and sigma xx will produce moment about this axis. So that is how it is moment about positive y-axis. So moment per unit y length about this is about the negative x-axis, negative x-axis. So same way you can also have actually myx. So we will check that myx due to so now tau yx here is going to be in this direction, so this would be tau yx, and when you multiply by dz and into z, so that would produce moment about positive y-axis. So this is moment per unit x length about positive positive y-axis.
Hello, sir.
Yeah,
Sir, how that mx y moment will be about negative x-axis? How will we decide that negative or positive?
for mx you are saying, no? So see, now if you look at, we are
Sir,
taking
for
this
mxy.
mxy, okay. So now if you look at mxy, this is the tau xy as you see in this figure, and when you take the moment of this force tau xy into dz is the force, this force acting in this direction here. So you see that it is going to produce no the if you let me draw it separately. So basically this is the phase, and this is the phase, and this is how your tau xy is there, tau xy, and you are taking a differential length dz, and then this distance from here to here, this distance is z. So when you multiply this force, this force is going to produce, if you look at this axis, so it will produce the moment like this. So that is how I'm saying this is moment per unit y length, of course, because this is on the y phase having normal along x direction, so the length is varying along y. But this moment is about positive, about the no the moment, this moment is going to be about negative x-axis. Is it clear? So this tau xy produces moment about this axis, and this moment is about the negative x-axis as per the right hand triad. So is this clear? Is it
Yes, sir.
clear?
So
Tau
actually,
xy into tau xy into dz into z will give a moment like this. And as per the if you use the right hand rule, so this moment is about this axis, which is negative x-axis. That is how I am saying that mxy is the moment per unit y length about negative x-axis.
okay, sir. According to right hand thumb rule.
Yeah, yeah. And the
Okay, sir.
stress we are taking as positive. The stress we are taking as positive. Sigma xx, sigma yy, and tau xy.
Okay, sir. Okay. Thank
Yeah.
you.
So yeah. So these are the moment resultants. So after we define the moment resultants, then now see the our ultimate goal is that in this case you will see that it is easier to write the know the total potential energy functional. So that is what I am going to write, and then we will discuss the finite element formulation for this plate, classical plate based on that. So we need to look at the strain energies now next. So if you look at the strain energy, for example, now, so the strain energy, so strain energy pi, I am denoting that by pi. So pi will be half integration over volume of the plate, and then we will have three pairs of stresses and strains are non-zero. So sigma xx into epsilon xx plus sigma yy into epsilon yy plus tau xy into gamma xy dv. So this is the the expression for the strain energy. Other pairs, although let's say epsilon zz is non-zero, but sigma zz is assumed to be zero. So those contributions are zero, and anyway tau xz, tau yz, and the corresponding shear strains gamma xz and gamma yz are zero. So these will only contribute to the strain energy. So now this can be written as this integration can be split into integration over the area in the xy plane and integration through the thickness. So minus h by 2 to plus h by 2. And then I can write this this whole thing either as sigma xx into sigma yy into tau xy, then transpose into epsilon xx, epsilon yy, and gamma xy. So I can write that expression like this, and then the integration through the thickness and integration over the area in the xy plane. So you can write it like this. Now what you can actually do is you can write the stress in terms of constitutive matrix into strain, and strain we have already expressed in terms of the derivatives of w, second derivatives of w. So you can ultimately write this as half, and then the integration over the area in xy plane, integration with along the thickness direction, minus h by 2 to plus h by 2. Then sigma, this sigma matrix is c into epsilon, so its transpose would be epsilon transpose into c transpose. C is symmetric, the constitutive matrix. So this will be, and the strain is, the strain you see is nothing but minus z, and into we have this del 2 w by del x square, del 2 w by del 2 w by del y square, and del 2 w by del x del y twice. So this is the strain, and in between you will have the its transpose, of course, because it is epsilon transpose. So this z scalar is taken out, and this is written as transpose. We are just putting the values of epsilon xx, epsilon yy, and gamma xy in terms of derivatives of w. And then the constitutive matrix for the plane strain case, plane stress case is 1 minus e upon 1 minus nu square into 1 nu 0 nu 1 0 0 0 1 minus nu by 2. So this is the constitutive matrix. And then we have minus z, again the strain epsilon epsilon, and the epsilon is del 2 w by del x square, del 2 w by del square, and twice of del 2 w by del x del y. And then here you will have, of course, dz dA. So this is the strain energy, what you can say. So finally you can say the strain energy pi will be, now you see W is the only function of X. So we have this Z minus Z into minus Z is Z square. So we will have integration of Z square, which will become Z cube by 3, and when you put the limits minus H by 2 to plus H by 2, it would become H cube by 12. So you will see that we get here EH cube by 12 into 1 minus nu square. So then we can actually write this as integration over the area, and Z integration is eliminated. And then you can see this is del 2W by del X square, del 2W by del Y square, twice of del 2W by del X del Y transpose. And then here in between no, you can take EH cube by 12 1 minus nu square inside this constitutive matrix. So you can write that as D nu into D 0, and then you have nu into D 0 0 0, and then we have 1 minus nu by 2 into D. So this, and here no, in this place you will have the strain terms del 2W by del X square, del 2W by del Y square, and del 2W by del X del Y twice here. And then here no dz, dA, only dA now, no dz. So this is the strain energy for the plate, classical plate. So this is finally the expression for strain energy as you see over here. Then if we look at the expression for total potential energy functional, so now we can talk of total potential. Hello, am I audible?
Yes, sir.
Yes, sir.
So are there any questions, doubts? No, you can stop me in between if you have any question or doubt in any step. So total potential energy functional, or the no integral functional. This will be now consisting of strain energy and the potential of externally applied distributed forces. So what I am going to consider is that when we are taking a plate, so the plate is one is that plate is subjected to distributed force along the z direction. So this is q, the coordinates of course, this is x, this is y, and this is z. And then on the boundaries, so the boundary, let us say we have the the shear force term per unit length of course. So this is let us say Vn, n is normal. So depending on x face, y face, and negative x face and negative y face, you will have this Vn. And let us say we also have the moment. So the moment is let us say this is the moment Mn. So this moment here is about the y axis. So let us say this is Mn, and this Vn and Mn are there on all the four boundaries. So under this case, the total potential energy functional I will be strain energy minus potential, that is plus the potential of these externally applied forces. So integration over area, the strain energy is del 2W by del X square, del 2W by del Y square, twice of del 2W by del X del Y transpose into, we have d nu into d 0, nu into d 0 0 0 1 minus nu into d by 2 into del 2W by del X square, del 2W by del Y square, twice of del 2W by del X del Y. So this is z axis over here, and this will be dA minus the potential of, so W, if you look at this Q, so over a small area dA, this would be, force would be Q into dA into W, the displacement along z direction will give you the work done, and negative of that would be potential, and then you integrate over the entire area. So the integration over area and W transpose, W is scalar anyway, so I'm writing it as W transpose into Q dA. So this is the potential of externally applied distributed load Q along the Z direction, and Q is force per unit area. Now this Q is force per unit area, and then you have these boundary forces Vn and boundary force Vn and moment Mn. So we do the integration over the entire boundary. So Vn is the force per unit length. So Vn into ds will be the force into W will be give you the work done. Negative of that will give you potential. So the minus sign I have put inside, and then W transpose into Vn, and then this Mn will be corresponding rotation. So the rotation would be del W by del N. So let's write as a transpose into Mn into ds. So this is the potential of the all the external applied loads. That is Q, force per unit area. Vn is the boundary force per unit length along the z direction, and Mn is the moment on the boundary per unit length again. So del W by del N into Mn gives you the work done, and then negative of that gives you the potential. So this is the total potential energy functional for this problem. So if you see here, as I
Yes, sir.
said, this, yeah.
Sir, can you tell the sign convention for Vn and Mn?
So the sign convention is that here the outward normal, this is actually n I am taking. So it is Vn is along the positive z direction is positive, and Mn, as you see, it is actually positive about the negative y, tangent direction. So if this is normal, this will be t tangent. So Vn is positive along positive z direction on a positive phase, and Mn is positive about negative tangent. So this, if this is n, this is t. So that Mn is about negative t axis.
How to find positive t-axis, the direction of positive t?
Yeah. So if we identify, let us say we have n is normal along positive x, then positive t I am taking along the positive y direction, and you
Okay,
will
sir.
have to move in that direction. When you are going along the boundary, then you have to, and if you are going from here along positive y axis, then you will move along negative x, and then you will come to this corner, then you will move along negative x. So you have to define the tangent in that along positive s direction.
Okay, sir.
So now if you look at, this is nothing but potential of distributed force Q. So this term is potential of distributed load Q, and if you look at this is the potential of boundary forces boundary force and moment.
Sir,
Yeah.
sir, when we see on a negative phase, then is V and M positive along the negative and means the negative z-axis and negative
Yeah,
t?
so now see, if you are taking, let us say, this phase, so here this will be n, and your t will be in this direction. So this will be n here, and this will be t. Is
Okay,
that
sir.
clear? Yeah.
And V will be positive along negative z.
Yeah, v will be positive along negative z. Yeah, positive v will
Okay,
be along negative z.
okay,
Yeah. So now once we
Sir,
have defined, yeah, any other question?
yes, sir. So
Yeah,
here we are writing Vn and Mn.
yeah.
So are these like when we cut a section and then we write the shear force and moment, or are these
Yeah,
something which
so
we have
fine. Yeah,
applied?
yeah. So this is, when you are writing this for the entire plate, so these are the forces and moments on the boundary of the plate. But when we talk of a finite element, so then it is in a particular element. So there would be adjacent elements to that element. So these V and Mn would be the reaction from the adjacent elements.
Okay.
Yeah. So now if you come to the finite element formulation, so we
And
will have,
hello, sir. Sir,
yeah.
what is the term del W by del N?
Del W by del N is the derivative of W with respect to normal. So for this phase n is x, so this would be del W by del x. But when you are talking, say for example, this phase, so this will be n would be y, so it would be del w by del y. For this phase, it would be again del w by del x. So like that. So it is derivative of w with respect to normal axis.
Okay, sir.
So now when we go for the finite element solution approximations, development of the element level governing equations. So one of the important thing is the the approximate solution. So when we assume approximate solution for the development of finite element, so what are the things we need? So you see that no, the this integral functional, the variable is only w. So we will be assuming an approximate solution for w. Now w, now if you see in the integral functional, so the highest order derivative of w is second derivative with respect to x and y, and the cross derivative, of course, x and y derivative. So if you look at the no one requirement for the approximate solution is that it should be differentiable up to the highest order derivative present in the integral functional. So now you see that from the differentiability point of view, the approximate solution should be differentiable at least twice, at least twice with respect to x and y. So that is the differentiability requirement. Minimum requirement is that whatever approximate solution we assume, it should be differentiable twice with respect to x and y, so that we can substitute it in the integral functional. Then second is that it should be a complete polynomial. So whatever is the highest power term we assume in the approximate solution, so all the lower order terms should be present. So it should be a complete polynomial. No, we are of course discussing the polynomial based polynomial approximate solutions. And third is the geometrical invariance. If we interchange x and y, the form of the approximate solution should not change. So geometric invariance, I have discussed this in the last class also. And the fourth most important thing here is that now the primary variables will be w, del w by del x, and del w by del y. So how do we identify that? Of course, we have not talked about the integral functional and the weak form. So we look at, basically these are the displacement quantities. So if you look at over here, now when we look at these displacements, so you look at all the geometric quantities. So w is anywhere displacement, so that would be a primary variable. And if you look at the in plane displacements u and b, those are also geometric quantities, but they are defined in terms of del w by del x and del w by del y. So del w by del x and del w by del y are also primary variables. So that means when we talk of the inter-element compatibility requirement, so these w primary variables, that is w, del w by del x and del w by del y, they should be continuous across the element boundaries. So we require the continuity of the inter-element compatibility requirement is continuity of primary variables and what are primary variables in this case? W, del w by del x, del w by del y. So these should be continuous across the element boundaries. So across the elements, wherever the boundaries are shared by two elements, so there from both the elements we should get the same distribution along that boundary, same distribution of w, del w by del x and del w by del y along that boundary. So primary variables should be continuous across the element boundaries, across the element, say, faces, boundaries or faces. And if we have such an element, if we can formulate such an element, so that element is known as compatible or conforming element. So this is called as compatible or conforming element. So this is known as compatible or conforming element. Compatible means it satisfies the compatibility condition, that is why compatible. And conforming is also same, that it conforms to the minimum continuity requirement of W del W by del X and del W by del Y. We also call, because in this case we require W as well as its first derivatives continuous. So this is also known as C1 continuous element, because W as well as its first derivatives. So this C1, C stands for continuity, 1 stands for the order of the derivative, so first derivative. So it is known as C1 continuous element. And now if all the continuity requirements are not satisfied, then the element is called incompatible or non-conforming element. So if all the continuity requirements are not satisfied, maybe some, maybe say in one phase W and del Wi, del W by del Y may be continuous, but del W by del X is not continuous. In the other phase, W and del W by del X are continuous, but del W by del Y is not continuous. So that kind of elements may be there. So for those cases, if all the continuity requirements are not satisfied, then that element is known as the element is called incompatible or non-conforming element. So the element is called incompatible, that it doesn't satisfy the compatibility condition. Incompatible or non-conforming element. Yeah, so now so this is now based on these criteria we have to formulate the elements. So let me take an as an example. Let us and I will discuss this in the physical formulation in the physical coordinate system itself first. So let us take a 4-noded rectangular element. So now,
Excuse me, sir.
yeah,
Sir, can you please explain again what is C1 continuous element? What does it mean? C1.
yeah, C1 continuous. See, now in this case, as I said, the primary variables are W and its first derivatives del W by del X and del W by del Y. So if element requires that variable as well as its first derivatives should be continuous across the element boundaries, then that element is known as C1 continuous element. C means C stands for continuity and superscript 1 stands for the order of derivative. So in this case, we required no the first W as well as its first derivatives to be continuous. So that is why it is known as C1 continuous element. Is that clear? C
Yes.
stands for continuity, 1 stands for the order of derivative. So because this element requires W as well as its first derivative to be continuous, so that is why it is known as C1 continuous element.
Yes.
So now if we talk of a 4-noded rectangular element in the physical coordinate space. So let us say if I just sketch the middle surface of the element. So this is the element, this is the middle surface. So this is say XY and these are the nodes. So this is local node number 1, 2, 3 and 4. And this is of course your Z axis. So now if you look at the degrees of freedom, now we need that W del W by del X and del W by del Y should be continuous across the element boundaries. So for that now we need at least first these primary variables as the nodal degrees of freedom. So that means we will have W del W by del X at 1 and del W by del Y at 1 as degrees of freedom. Similarly at node 2 W2 del W by del X at 2, del W by del Y at 2. We require these as the degrees of freedom at the nodes. Similarly at node 3 you require W3 del W by del X at 3 and del W by del Y at 3 and similarly at 4. So now if you look at Based on this, total elemental degrees of freedom are going to be 12, because 3 degrees of freedom at each node, that is all the 3 primary variables, and 4 nodes, so total elemental degrees of freedom are going to be actually 12. So when we assume an approximate solution, that should have 12 terms in it. So that is 12 unknown constant in that, and there would be corresponding 12 terms in that. So when we look at the approximate solution, so I think I just explain you this, and then I will stop. So approximate solution means it should have 12 terms. Why? Because we have 12 elemental degrees of freedom. So there should be the corresponding 12 constant in the approximate solution. When we choose the approximate, write the expression for the approximate solution. So say W. So we look at actually what is known as Pascal's triangle. Pascal's triangle. I think space is not enough, so let me write it again. So as per this, that various terms we take is the constant term, then linear in xy, then x square, xy, and y square. Then we have x cube, x square y, xy square, and y cube. Then next row is x4, x cube y, x square, y square, xy cube, and y power 4. So like that. So this is known as Pascal triangle. So we choose the, now we need to choose 12 terms. So we take constant term, we take linear term in x and y, we take quadratic term x square, xy, and y square, we take cubic terms x cube, x square, y, xy square, and y cube, and then we take the quartic term. So in that we want to take x cube y and xy square, so that the form of the solution is geometrically invariant. And we give preference to the terms which are closer to the center of the Pascal's triangle, center line of the Pascal triangle. So in that case, W would be A0 plus A1x plus A2y plus A3x square plus A4xy plus A5y square plus A6x cube plus A7x square y plus A8xy square plus A9y cube and plus A10x cube y and plus A11xy cube. So this will be the 12 term approximate solution. And yeah, so of course, for formulating whole of the element, we have to say that at the first node xy is 0. So if you look at the x and y coordinates here, so at this node x and y coordinates are 0 0, and let us say this length is a, this is element length now I'm talking about. So this is a comma 0, this will be a comma b, and this will be 0 comma b. So now I know these 12 constants A0 to A11 can be expressed in terms of elemental degrees of freedom, W del W by del X and del W by del Y at various nodes. And then when you write that, you will get the 12 shape functions. And then of course we need to substitute this in the integral functional, and then take delta I equal to 0, we get the element level governing equation. So that's the procedure to get the element level governing equations. But next thing is we need to check the compatibility. So I think I will discuss about the whether the element is compatible or incompatible in the next class. So I will continue in the next class. So I want to stop here. If you have any questions and doubts, you can ask.
Sir, I don't have any doubt. I have a question regarding the book.
Yeah,
Actually, the Asghar Bhatti book, I tried
yeah,
to search for it online, but it is not available, sir. So, is there any other book we can
yeah.
refer
It may
to?
not be available online actually. Yeah, that's true.
Yes, sir, it's a hard copy actually. Even on the Wiley's site, it was like ebook was not present.
So I really don't know some ebook on this which is freely available. So other book is of course there is a book by finite element method by Jane Reddy. So basic book itself has a chapter on the plate bending elements. So I then you can refer to no finite element method book by Jane Reddy for this plate bending element.
Okay, sir.
Yeah. So if you have that book that has chapter on plate bending element, so you can refer that.
Okay, sir.
Yeah. So are there
Sir,
any other question doubt? Anybody has any question doubt?
hello. Yes, sir.
Yeah.
Sir,
Yes.
in order to complete the 12 term, we
Yeah.
take linear term, quadratic term, cubic term. But when we take order 4 term, we have
Yeah.
only two terms.
Yeah.
So we take x cube y and xy cube instead
Yeah.
of x cube power 4 into divided by 2 power 4. Why, sir?
Yeah. I just said no. These we give preference to the lower power terms. So now lower power terms means we are giving instead of x power 4 y power 4, we are giving preference to x cube y and xy square. So that is something like no, it is cubic in x and linear in y, linear in x and cubic in y. So we are giving preference to those variations rather than x power 4 and y power 4. So so that when the element is smaller and smaller, it accurately no it gives the exact solution. If you have x power 4, y power 4, so let us say the variation of w which is proportional to x cube and in the y direction y, that would be missed out. So we want to give a preference to that. So we give preference to the lower terms compared to the higher power term.
Sir, then why did we not include x square y square?
Yeah, we
Like if
cannot include. As now the problem is we cannot include that because we want to have a 12 term approximate solution. So if we include x square y square, then that's only one term. And then other term if we include, so either we will take x cube y or xy cube, so the form of the solution will be geometrically it will not be geometrically invariant. So to satisfy that requirement, we are taking this geometrical invariant. And if you look at this term, actually gives the quadratic variation both in x and y, whereas these x cube y and xy cubes give linear variation in the other direction. So like here y linear in y, linear in x. So linear is given preference than the quadratic. And also to satisfy the condition of geometric invariance, we need x cube y and xy cube,
okay, sir.
both these terms.
Hello, sir.
Yeah.
Sir, could you please re-explain that potential of boundary force and momentum?
Yeah, so what I said is that when you look at the either the plate boundary or the element boundary, so I said now because this is integration over the entire boundary, so the normal and tangent directions are going to change. So here I said that on this face, let us say this is the normal and this is the tangent, and no your s is measured from somewhere. So let us say this is the direction of s, it continues from here, then this will be direction of s, it would be going like this, and here this will be direction of s, it would be coming over here, and this will be, so that is how this s will be there. So on this face, on the this face n, where it is n is along the positive x direction, the we are assuming that there is a positive boundary force Vn. So this is your Vn, and then there is a positive moment about basically negative t direction. So you have the moment like this, moment like this. So why I have taken it like that, so that the potential of both of them are negative. So this is your actually Mn. So now the work done by Vn is going to be Vn into W, because Vn is in the W direction, the displacement force in the direction of W. So work done is Vn into W, and then potential is negative of that. So that is how I have written the integration over the boundary minus sign, and then I had said W transpose into Vn. And then now if you look at the Mn is the moment about negative t axis, and del W by del N will be when you look at del W by del N, so you are taking derivative with respect to del W by del N. So when you look at del W by del N will be in this direction, del W by del N. So you look at this del W by del N and this Mn, they are in the same direction. So the work done would be Mn into del W by del N, and then the potential is going to be negative of that. So I have written that as del W by del N transpose into Mn ds. So you are assuming in this case that Vn is along on the positive phase, it is along the positive z direction, and Mn is about the negative t direction, and based on that, this is the expression for the potential. Now, depending on the actual forces on the boundaries, Vn and Mn may be positive or negative depending on which boundary and in which direction these are there. So the basic idea is that Vn is in the direction of W, and Mn is in the direction of del W by del N, and del W by del N, then del W by del N in this direction. How do we come to that? So this is the along N direction. So N direction, let us say we have some W over here. We assume that the W is increasing along positive N direction. So here the W would be the higher. So if you look at the rotation, is now from this to this is the rotation, so it is in this direction. So that is how I said that del W by del N direction would be like this, and therefore the potential will be like this. So is that clear?
Yes, sir. Thank you.
Yeah. So are there any other questions? Anybody?
Sir, here, does the direction of integration matters? Like, how do we take into account the direction of S?
Yeah, so the direction of S I am taking. So suppose for the plate or the element, if this is the I am taking basically in the, you can say, counterclockwise direction as positive direction for S. So I am traversing the boundary like this. See, the basic idea is whenever there are forces in the boundaries, you have to see whether they are in the direction of W, V is in the direction of W or not. If it is in the direction of W, then the potential is negative. Similarly, when you look at the Mn, whether it is in the direction of del W by del N or not, and if it is in that direction, you take it as, the potential as negative. And the others you can take as positive potential. So that's the basic idea.
Okay, sir. So if I reverse the direction of S,
Yeah.
then integral will become negative or it will remain same.
You have to again, so you will also be changing the directions of Mn and del W by del N. So even if you change the direction, if you are using the same directions of Vn and Mn and also the W and del W by del N, then this integral will remain same.
Okay,
Because
so
S, yeah,
T is always along S.
yeah, T is along S, yeah.
Oh, okay, sir.
Yeah. So anybody else, any question? Okay, so if there are no questions, I am stopping here. Thank you all for your attention.